we will move to the next subchapters for this number 7, solving calculus problems. So we will, depending on the contents within the book, this book to see is whether we can combine some chapters altogether in one video. So for this chapter, I hope we can discuss the not too many contents about this SymPy assumption, because that is an assumption used in the calculus problem discussion, so that we know what we are going to use, and then we also take time to talk about how to find the limit of the functions. So then we try to combine these two, and let's now go to our book. So in our program, so we have this as our program. Let me clear that. We create a symbolic link in SymPy. So these are the symbolic link in SymPy, and define the variable as the x, and assume that as a result of our operation to ask SymPy to do the solve. SymPy need to check whether the expression is okay. So that is our last part. But this program is we will check is whether x plus 5 as the input is more than 0. So let's see what would happen. So let's use our Python directly. So from SymPy, let's from the scratch is SymPy import symbol. So we only have a single symbol. So just use this capital started symbol, and we define x as the symbol with single quotes. Then you can type x is our symbol. So if x plus 5 more than 0, we want to print do something, and else we want to print do maybe nothing. So let's see, we got this also the expected traceback, but possible is depending on the Python's this version. So let's see. So I put that here. You can see the exact content maybe not the same, but what the most important is give you this last line. What is the arrow category? It's a type arrow. I think it's in the version that the author uses to like mention is cannot determine truth value of. So here is we have our some this more relevant is cannot determine truth value of relational. So relational is now is we want to check this Boolean value is we do the relational operation. So then they are not popping up this one, and it's coming from the different contents, but the source code is relational Python. So if you want to see here, so let's see. So if you are really interested to learn the this source code, you can come to this relational.py to get here. So if this one happens define like this self, then it's raise this type arrow. So that is the anyway. So here we got some errors. What's the reason? So because SymPy doesn't know anything about the sign of x, because we only define x. X is our symbol, but is x equal to 1 or equal to 100 or equal to negative 100? If it's a negative 10 or negative 100, x plus 5 is still negative, so it's less than 0. But if x is a positive, it will be more than or larger than 0. So that will be true, and earlier will be false. So if a Boolean is cannot determine the exact value, then it will popping up this arrow. So because of we are using the symbol. So it's called deduce whether x plus 5 is greater than 0. So deduce means is we put this simplified result. So we should decide what exact meaning or value for x plus 5, but we cannot. So it's the displayed arrow. But basic math tell us is if x is positive, x plus 5 will always be positive, and if x is negative, it will be positive only in certain case. So in certain case means is if x is larger than minus 5 or negative 5, x plus 5 will be more than 0. So that is the way is if we give this symbol with some condition. So if we put here, so let's see if when we define x, we will put this positive is true. So now we define our x with our positive. So then is if so we can no need to retype that. Let's just see x plus 5 is more than 0. Then I got true. If we don't do that before, so let's see. Earlier is I have our x is this one. So if I do this, so I just get this symbolic expression is just like is equity expression, but they cannot what we call this term is the deduce. So, but once I define x is our positive, then I can start to see x plus 5 is 0. But if I put is like it's negative, oh sorry, then I put here, I can only get our expression because it's not able to deduce. So why? It's because you only see it's a negative is not enough, because the negative 5 to 0, it can still make this expression true, and only the x is less than the 5 or equal to 5, negative 5 is can make this false. So if so, in that case, is again you cannot make those deduced. So that is the what we put is the when you do this this SymPy to define a symbol, you can give a certain assumption for this symbol. But this assumption is very the rough assumption, just a positive, negative. So that at least this classification, the declarations we have now learned additionally in symbol is called this assumption in SymPy. And then let's move this third part is try to find the limit of the function. So a common task or the when you once you finish learning the functions definition within the calculus, the teacher will teach you this chapter. So to find the limit value of a function. So limiting value, or simply as we call this a limit. We use this symbol and put this variable equal to approaching to some direction. So when the variable's value is assumed to approach to a certain value, that is our limit. So let's consider this 1x. So x always 1 divided by x. Let's see what's this limiting value. So limiting value is we know is 0. So why is when x is approaching to the those infinitive max, then that will be the 0. But if x is approaching to 0, so this is the x y coordinates, and then this will be the positive maximum or infinitive. So that is the two limiting value. So how the SymPy can do that is we can test this. So from SymPy, we will import limit. So like symbol, limit is we started from capital L. And we already have a symbol, so and we will import S. So S is the specific class or contain the definition of infinity. So positive infinity, negative infinity. So it's this symbol. But this symbol is quite interesting. Is when the Python try to plan that, is just to put two small o together. Actually, this like our number 8. You put that lay down. So that, but here is when you see the double O is means the infinity. So we have the limit, we have the symbol, we have this S class including the infinity. Then we can have the over X. Let's redefine X without those assumption. So X is just this one. Then the usage is we put this limit, and we could look at this. So first we have the expression, so 1 divided by x, and then the second is this variable is x, and then we give is the x approaching 2, so approaching to the infinity. Then what we got is it will tell us is the limit x 1 divided by x, and infinity. This dr direction is approaching from the negative. So dr is specify where is the approaching direction. So because we are approaching the positive infinity from the left, then that means is dr is negative. So from the negative side, and then is how we can get this result. So we will introduce now is this dot, and in the later is we'll keep using this dot. So that is a method. So that ask this expression to do the testing, the calculation. So if we put this into our L, then we can just use this method is dot, then we got 0. You can also directly use this and dot. You will also get 0. So that means is you put this when it's approaching to the infinity, you get 0. And if you see is I want to approach this to 0, so you will get positive infinity. So and you can see here like here. So now you see if you approach 0 for this line, you approach from the positive or from right, then here the direction is the positive. So that is the difference. But in this book, they didn't show you this one, but you can test yourself. And here is we calculate this one is here you can see that. Then the limit class also handle the function with limits with indeterminate form like this one, so infinity. So from here is we can see is from SymPy. We already import a symbol, then we just adding the sign. So and we see the limit sign x divided x and use x as the variable. Then we do this dot is 1. So we can use this way later on is when we package on these derivative parts. So let's see. So we may have continuous compound and also the instant rate of change to do this testing. So these are the two samples, but we just use the terminal to calculate that. So consider you deposit $1 in bank. This deposit is the principal. So your principal is $1 in the bank, which pay you the interest by bank. So and we need to know the interest is 100% that combined n times the years for yearly for 1 year. The amount you will get is this amount, and is 1 plus this the times of this interest calculated, and then with this summary you get these squares with n. The prominent mathematical is called James Bernoulli discovered the formula. So value for n is approaching to our interesting constant we call the e. The natural the constants or the constant that we can verify by finding the limit of this. So we have the impulse symbol s both already loaded, so we can directly build over n symbol. And then this we put this limit. So let's see. So we create this as b maybe. So b is equal to limit is this expression is 1 plus 1 divided by n and squared n, and variable is n and approaching to the infinity, positive infinity. Then what is b? B is like here. So when we go to the positive infinity, is approaching from the negative side. So that is the far part. Then is let's do the b dot. So we got this e. So and we see e. We cannot directly print. So that and I think it's let me see. So it's just our e. So that is not printable, but that is the cost. For any principal amount p, any rate is r. So we have this year t. So then we have this combined the formula. So we have all of them. Then we can see p symbol positive. So let's see whether we can make this assumption altogether in symbols. So import symbols. So I want this PRT, our symbols, PRT, and together give them positive is true. Okay. Oh, sorry, it's true. So that means it's also work. You can do this line by line, or you can do this all together. So let's verify r more than 0. So because it's positive, so it's true. R is equal 0 is r equal 0. We gave is r is 0. So this sorry. So I should retype that. And r is a symbol, and r is a double equal. So that's false. So which means is r less than 0 is false. So we got this assumption is work. Then let's make this our expression now is getting this complex. So I see is c is limit, and is p times 1 plus r divided by n. So just ensure you type this correctly. So n times t. So, and then this over the expression, the variable is still n, and do this the positive infinity. And oh, so what's the arrow? So p. Oh, infinity. So I have the typo. So let's say c. So it's this is our expression and variable, and here is the positive infinity and approaching from the negative direction. Then let's do the c dot. So we got this p times express square and with this r times t. So that is the our continuous this combined interest. And then when we see is we can do another sample is instantaneous rate of change. So consider car moving along a road. It accelerates uniformly such that the distance travels. So we have this s is the distance, and they have this actually it's t times it give you the acceleration, and the t is give you the velocity. So this is are the two levels of this variable. So in this function, the independent variable is t, which represent the time. If we measure the distance traveled in time, then the time between time and t1, t2, such as the t, and we assume t2 more than t1, then we can calculate the distance moved by the car in 1 unit of time using this expression. So s t2 minus s t1 divided by t2 minus t1. This is also referred to as the average rate of the change of function st. And then this we will have this epsilon. I think is the difference between the or we see the delta between t1 and t2. Then when we have this delta, we can have this expression try to see when this delta is approaching to 0 and what's the results we can do. So let's do this test. We have this expression and we want to approaching to 0 now. So we have all these input already. So what we need to do is we need to define time. So time symbol is t, and then this we have st. So it's just capital S, small t is just is our the expression. So that is fine. So st is 5 times t square 2 plus 2 times t. Don't use 2t, so that is not valid. Parts is then we say t1 is symbol, another symbol t1, and then we see the delta t is the another symbol. Then is st1 is the st is we send the oh so sorry is so I should have this code, and delta t is okay. So t1 is the symbol now. So st1 is just send the variable. So st dot subs, use this t1 to replace the t. So t1. So then we got the st. So let's see st1. So is this one is replace t by t1. So then st1 delta is equal to st dot subs, use the t by t1 plus delta t. So then let's see is the delta. So we have this one to delta is they put this in the back. Then what we can do is we send this the s the new s is the limit. Then is we have our expression. So st1 delta minus st1 divided delta t, and the variable is delta t, and approaching is to 0. So now let's see. So what's the expression looks like? Is make that bigger. So this is our expression now, and delta, and approaching from the positive part. Then is we can see new s dot we will get 10t1 plus 1 plus 2. That is the limiting value. So that is another sample for this. So I hope it's again, this is not a mathematics the course, so you can back to your the mathematical workbook to find this, and I hope it's you get some basic ideas on the limiting value calculation using SymPy. So and that's conclude this video, and we will move to next video is for 7.4. So see you then. Bye for now.